Hi, kids. All right, we're doing problem 5 on the Bohr model worksheet. But here's the important information from the problem. It says the ionization energy for this atom is 4.1 electron volts, and then it has emission lines of 310 nanometers, 400 nanometers, and 1377.8 nanometers. Okay, so and you're supposed to create an energy diagram from that. So we know that our energy well n equals 1 is going to be equal to negative 4.1 electron volts. Okay. So then where do we go from here? Well, we have these in wavelengths, so we are going to have to figure out the corresponding electron volts that go with that. So to do that, we are first going to have to use C equals F lambda, and I'm going to just step through this one, and then you guys can work through the others. But when you do C equals F lambda, C is 3 times 10 to the 8th. F is what we're looking for because we have E equals HF, and then this is going to be 310, and nanometers is times 10 to the minus ninth. And if we do the math, okay, I already did the math. My frequency comes out to be 968 times 10 to the 14th hertz. Okay, then you have to do E equals HF, and because we want this in electron volts, because this is in electron volts, I want to pick the H that is in electron volts. If you look on your formula sheet, you will see it's that. And then when you do this, you get an energy that is 4.01 electron volts. Okay, and then you have to do the same thing for the other ones. And when you do the same thing for the other ones, for this one you get 3.11 electron volts, and then this one you get 0.9 electron volts. Okay, all right. It is really important, though, when you are solving these problems that you show your work on what you're doing, because that's how you're going to be doing it. So you would want to show your work for these two as well. I'm not doing it just to make this video not last super long, okay? All right. So we have this, this, and this. Now remember, it's an emission line. That means I am going from a high energy level down to a low energy level. So I'm going to be going like that or something in between. The other thing to keep in mind, remember that the first jump is the biggest. Y is the first jump, and then the next jump is going to be the next biggest, and so on. The reason that has to be is, remember, what does this mean? This means you're closest to the nucleus. So to jump away from the nucleus is going to be most difficult when you're close, and then it's not going to take as much energy for the next one, and so on, because you're getting farther from the nucleus. Okay? All right. Now let's actually look at these numbers. All right, 4.01, 3.11, 0.9. Are those numbers related? Oh, wait a second. Yeah, they are. This plus this equals that. That's an important thing to notice. So if you think about, well, if this plus this equals that, well, then it should kind of look like this. Oh, so I should have this, and then I'm going to have this. Where guess what? So these are going to be my different energy levels. Where this big jump would be 4.01 electron volts. This jump would be 3.11 electron volts. This jump would be 0.9 electron volts. The other thing to keep in mind, okay, that you have to remember, this jump, this thing has to be the biggest, and that's the next biggest, and so on, which is why I had to go this way. So if I call this n equals 2 and n equals 3, well, then you pretty easily can figure out what all these numbers should be. So if I take 4.11, or sorry, 4.1. 4.1 minus 3.11, you get 0.99, so this is going to be negative 0.99 EV. And then if the difference is going to be this, that means this has to be negative 0.09 EV. Okay? And then I have just constructed my thing. Okay? But again, picture, math, have it make sense to you. Make sure you can do the words. All right, now you should hopefully be able to solve the rest of those. Bye, kids.